So Aril, Karthik, Sunil, I mean, how is your confidence level on regression? So based on that, what we can do is we can think of either now we can start from the beginning, or we can just have a question answer session.
I'm familiar with linear regression actually.
Mhm.
Like, yeah, I mean, the linear regression part I'm okay, but it's better if I get some brush up on that again. And
Okay,
multiple regression, actually, I want from the start.
okay. So multiple linear regression, you are not aware, right? I think he also might have not taken it. I'm
Yeah,
not
yeah.
sure. Okay. So what about Aril, Binod, and Sunil? You guys are familiar with linear regression?
Yeah, Lakshmi. So linear regression is fine for me, but multiple regression, who Karthik said that like we need to start that over. And one more thing is that last class he did something on R programming also, like the whole that also I was not able to understand properly. Like, for example, we should plotted some graphs, 3D graphs and all that. So I was
Okay.
not completely satisfied with the understanding of that also.
Hmm. Okay. Yeah, Sunil and Binod. Yes,
Hi,
Sunil.
Lakshmi. Uh, Lakshmi, it would be better if you just give a recap of it because I have not attended the class, just I have heard it.
Okay. Okay. Hmm. Okay, fine. So, yeah, I think it will be same with the Sunil also, because both of you, Sunil was also missing in the class.
Lakshmi, I'm good with linear regression. Um,
Okay, fine then. So let me do one thing. I'll just quickly go over the linear regression and what are the areas
Hello,
you should.
Lakshmi, can you hear me?
Yeah, now I can hear you properly. Yes, Vinod, go ahead.
जगह लेके छीट के सोता है 10 आदमी का
Hello. Fine, guys. I mean, it's okay. I understood. I mean, so everybody can clearly hear my voice, right?
Yeah,
Just
Lakshmi, we can.
okay, great.
Yeah,
Fine.
yeah, Lakshmi.
Yeah. So let me share my screen. Just guys, mute yourself. Okay, all of you mute yourself. If you want to talk, then unmute it and then talk. Okay. So, but there is a lot of disturbance in the background. I'm going to mute all of you. Okay. Fine then. Yeah, this now it is better. So let me share my screen. Okay, so all of you can see my screen, right? Just respond on the chat window. Hmm. Okay, so we have understood. We have gone through the ANOVA model, right? Once in ANOVA model, what we have tried to understand, we try to understand if there is any relationship between two variables, right? So what are the two types of variables? One is your continuous variable, another is, yes, another is categorical variable, isn't it? So which one is the categorical variable? uh, there is an independent variable and there is a dependent variable. So the dependent variable is a continuous variable and the independent variable was a categorical variable. So when the category is change one to another, is there any change happens on the continuous or dependent variable? This is what we have tried to understand. Now let's take an example. If your the independent variable becomes a continuous variable instead of categorical variable, right? So now let's see how I can establish a relationship between your dependent variable and independent variable, and when these variables are completely continuous variables. Okay, this is what I try to set up. Okay, let me take a paint. Okay, say let's take some examples. Anybody can give example for the a relationship between one continuous variable to another continuous variable. Hmm? Is
Height and weight.
Yeah.
yeah, I just took age and salary. Yeah, so okay, so yeah, now why we say it's a regression when there is a change happens in my y variable. This is my y, is when there is a change happens in my x variable, there is some amount of change happens on my y variable, right? And why I say it's a linear relationship, because there is a what happens, let me why it is linear regression is, it is called because it is related in a linear function, right? How y is equal to mx plus c, it's a linear equation, isn't it? Straight line, right? It's not necessary that every regression have to be a linear regression. Okay, so you can have different types of regressions like exponential. So here this is my y and this is my x. So how I can relate this one? Y is equal to, yes, can anybody answer me what kind of relation it could be? Y is equal to m,
e to power x.
Parabola. Parabola.
isn't it?
Polynomial.
Y is equal to, yeah,
Polynomial.
x plus x square, isn't it? So if it, because there is a positive, this is always positive, right? This is always positive, right? Now here, okay, m beta 1, beta 1 and beta 2, there will be always some coefficients. This will be like this: y is equal to m plus beta 1 x plus beta 2 x square. Okay, now suppose I can have also another regression equation. Okay, how it will be? Y is equal to m plus beta x square, right? Because always it is positive, right? Y is always positive, isn't it? So you can have different types of regression relationship, but in general most of the problems you will be finding kind of linear regression, like it is no uh, I mean y value increases or decreases linearly when there is a change happens in your independent variable. Okay, so let's take examples as like I have taken your salary and age. So when the age increases, your salary also increases. Is it always falls under a straight line? Not necessarily. So how we can depict whether there is a linear relationship between age and salary is there? We have already understood there is a collinearity, right? Collinearity we have already studied, right? Covariance and collinear covariance we have studied, right? The change happens in X and change happens in Y. How they are related? Is it positively related or negatively related? Covariance talks about like that, no?
Yeah, Lakshmi.
Right. Similarly, collinearity gives the how strength is the linear relationship between X and Y. So the strength could be a positive or negative, or it can be zero. So when the relationship 0 between X and Y by means of collinearity value, it doesn't mean that X and Y are not related. They might be related in a different way. Okay, only they are not related in linear way. That's what the collinearity will tell. Okay, now let's say I wanted to find out only linear relationship between X and Y. Okay, then I want to, yeah, so what I need to do is first I'll take X and Y and then I will plot them. Sorry, X. So here is your salary, and here is your, okay. So you might have seen that different age people, see, let's say you work in a single company and you have not changed, and your age and salary will grow in a steady manner, right? But what we are trying to find out, we are not trying to find out a single person's salary growth rate. We are trying to find out salary as a general, how it is related to age in general. So if you take let's say age, I can start with age 20 to 50. Okay, so you'll find in age 20, some some people's salary might be still zero, like almost equal to zero, still they are studying. But you will be finding some people are started earning some, some decent amount of salary, and some are into business and their salary is too high, right? Similarly, when your age keeps on growing, every age you will be finding different levels of salaries, right? Let's say, so you started getting like this, but you will find a steady growth, right? Okay, okay. So if you see here, what happening is this. Okay, so is there any relationship between age and salary? How we can do that? Now we need to plot a graph. Okay, we need to plot a straight line, finding whether this there is any linear relationship or not. So let's see, my straight line comes like this. Okay, I can plot a straight line like this, I can plot a straight line like this, I can plot a straight line like this, which is trying to represent the entire population. Okay, population in the sense it will try to represent every no point in my in this space. Okay, so what does it mean? It is trying to say that there is, in general, there is a a linear relationship between age and salary, and I can represent this relationship by a straight line. And this straight line, what it is trying to do is it will try to represent all the points in some in a in a me in a in a way that it will uh, try to minimize the error. Okay, so when I say try to minimize the error, let's say what I meant by that, I'll create a simplified graph and then I'll try to explain you. This becomes too much. Okay, let's say in 20 I got 2 here, something like this. Okay, okay, okay. So these are all my data sets. Okay, for different age and for different age, I got their salary variations. But it looks like the salary is increasing. Okay, let's say how I can represent this relationship. I can represent this relationship by plotting a straight line on it. Okay, I can plot a line like this, or like this. So when I plot this line, so I have option to choose either one of them. Okay, say line 1, line 2, line 3. Now since you have already taken the class, now tell me which line I should take to represent this relationship between salary and age.
The one which has the minimum errors,
Huh.
I
like
think
the
What
distance
what
is,
we do
between the
is
points.
yeah, what is that error?
The Now suppose if we take the first line, what is the difference of data between that line and the other points on that age group? So let's say 20.
Hmm.
If I take that first line, what is the difference between that between the other point and the line? So we'll have to
Okay,
add up all the errors like that.
okay. So what this line is telling, I can use this line and I can predict, right? I can predict when the age is something like 70, what could be the average salary of anybody whose age is 70, right? Since I have
Yeah.
converted to a no, linear relationship, I can use this linear relationship um, equation and I can predict what could be the salary. Similarly, if this line is represented, this line will tell that for age of 20, this is what the salary is expected. Okay, but actual salaries are, you can see here is one and here is one. Okay, so the actual is here, isn't it? It means that there is some error in prediction, right? So what is the error? Error is, this is what, let me take some, this distance is the error, right? This is what your error. So this error, what error is not only will be coming in age 20, it will be coming in every space, right? Every point. Now when you reach here, the predicted value is this, right? But actual values are this and this. So you add up this error, 1 and 2. Here also, see, here also you got some error. Actual is predicted is this, actuals are this. So every data point, every age value, you are making some errors, right? And this error should be minimized. If you minimize this error, then you can say this is the line which is best fit for my data set. Best fit for my data set means the data set which you have taken salary and age, and the salary and age relationship can be represented by a straight line, and this is the straight line which is giving you best fitting line information or minimization of your errors. Now how you can minimize the error? The errors are, if you see here y value, okay, y predicted, y actual 1, okay, y actual 2, y actual 3. So total deviation is what? Total deviation is y uh, y predicted, y predicted minus y, yeah, y1, yeah, plus y predicted minus y2 plus y predicted y3. Okay, so when you say this may give you positive, right, and this will give you negative, right, because ya1 and ya2 are bigger numbers, right? So this will give negative and this will give positive. When you all add up, the actual error which is contributed by this line will be nullified,
Zero.
or it will be zero, or it can be subdued. So that's why what we do is we square them, right? So you have to square these things and add them, right? For every age, what we are trying to do is we are squaring the error terms. Okay, just a second. Okay, so we will square all these error terms which is contributed by each individual data point, and we sum them all, and the sum of all the square terms, we will be trying to minimize it. Okay, how we will be minimizing? We have to come up with a equation or straight line equation which is going to help us, not straight line, regression equation, which is going to minimize the error contributed by each individual data point, right? So how we can do that? Let's say how I can make it. Let's say keep this, okay, y is my uh, predicted minus yi, okay, should be 0, isn't it? This is what my ideal case, right? Isn't it?
Correct.
Right. So what I can do is
Yeah,
y predicted. So how I can represent? See, y predicted is, I'm thinking it's a straight line. So what could be the straight line equation? Y predicted is nothing but the straight line equation.
mx plus
mx
c.
plus
Uh, m plus Tell me. Yeah, give me what is the equation you write?
mx plus c, you can write.
10x.
mx, like, or beta x plus beta 1.
Okay, or you can say, okay, b0 plus b1 x. Why I say b0 b1? Because b0 b1 we always get the samples, isn't it? The data what you have is a sample, right? From this sample I find they are having some kind of linear regression, and this linear regression I can represent by a straight line, imaginary straight line, and whose imaginary straight line that your what is beta 0 intercept, isn't it? And beta 1 coefficient of x, right? So what does it mean? So when y is equal to, I mean when x is equal to 0, you still have some salary. I mean here it means that when your a is 0, you still have some salary. Okay,
Yeah.
so sometimes you will find some values, right? Which is have a fixed value, like let's say your expenditure and your salary, right? So your expenditure also increases when your salary increases, isn't it? So if you're trying to represent a relationship between expenditure with salary, so you can also come across like when your salary is 0, you may be it is not like since your salary is 0, you're not making any expense, no, you're investing, or there is no expenditure from your end. You will be having some expenditure even though you don't get salary, right? So that's how this beta 0 value comes. Okay, beta 0 coefficient and beta 1 coefficient. So the beta 1 coefficient, what it talks about is whenever there is a change of 1 unit in x, the beta 1 unit of change happens in y. Okay, and in sample space, whenever there is a change of 1 unit in x, the b1 units of change happens in y, right? This is what the equation says, right? Now let's come back to the linear relationship where we are trying to minimize the sum square of error. Let's say y is equal to, I can put like beta 0. Okay, now beta 1 minus beta 1 x minus yi 0. Now I want to minimize the entire equation, will be minimized to 0. So how I can do that? What are the values which going to influence to make it 0? Beta, see, b0 is always constant, right? What I need to find out, I need to find out your, see,
b0
x and
b1.
yes, you will be x and y x, here this will be b1 xy and yi. These values are already there with you in your sample data. Okay,
Lakshmi, one
but
doubt
what,
I have.
yeah,
Yeah, for the ideal case, you have written a summation of predicted value, that is y cap minus y of I of a square equal to 0. So
mm,
is it telling that both the lines are equal? I mean the same line, so it is 0.
what is same line?
Like predicted line and the main line where we are predicted line which we have predicted, and the line which we are comparing to.
Which line we are comparing? We are not comparing any line, right? We are trying to find out a best fit line, okay, which can represent the entire relationship between x and y,
Yeah,
right? Now to represent, what I can see is there are, it cannot represent, okay, because there will be always some errors.
yeah.
right? For each age value you will find different types of salaries, right? But in general, age and salary, they might be related linearly. Okay, so how you will find out, I mean, which best fit line you can take which can give a better prediction or more accurate prediction. That's what my objective. Okay, so to get the best fit line, what I need to do is I need to minimize the sum square of errors. Okay, so when I go and try to minimize the sum square of errors, I reach to a equation like this. Okay, so in this equation I know xi and yi, right? Because it is there in my sample data. So what I want to know is beta 0 and beta 1. So for which beta 0 and beta 1, my equation like I mean my sum square of error is equal to 0 or almost equal to 0. This is what I'm going to find out. So I want to know, guys, I mean, is this clear?
Yeah, Lakshmi, it is clear.
Yeah,
Yeah, like,
good.
Yeah, Lakshmi.
Right. So now what I'm going to do is I'm going to make something like partial derivation, right? Partial differentiation. Okay, dy, yes, partial differentiation with
excess constant. Excess
D,
constant.
I'll
dy
keep
cap by x.
x and y is already there. So when yeah, sorry, let me see what is that. You have to, okay. Let me put that here. Okay, see, this is what you partial differentiate with b0 and b1 and get the value, then you will find b0 and b1. So what I'm trying to do is I will keep um, b1 is equal to constant, then partial differentiation with b0. Okay, partial differentiate with b0 to get b0 value, and partial keeping b0 constant and partial differentiate with b1 get the b0 value. This is what I try to find out. So let's say if you differentiate with b0, okay, and keeping b1 constant, you will find for which value of b0 you will be getting the equation is tending to 0. Okay, taking the derivative with respect to b0 and b1 set to 0 and solve for b0 b1, we get the least square estimates. So this is just you try to keep b0 b1 in a state that keep b1 constant, partial differentiation of b1 b0, and keep b0 constant, partial differentiation of b1, both all together going to give you the values of b0 and b1 for which the entire equation is going to be 0. Okay, this is what it is telling. So I mean, this is part of maths, you just need to understand, you don't need to get into the details. Ultimately it is trying to minimize the sum square of error, okay, by providing the values of beta 0, b0 and b1. Say why I say b0 b1, because this is only applicable for the sample data set what you have taken, right? Now if your sample sizes increases, okay, then your b0 and b1 also will change. Okay, so now you got b0 and b1 now, but b0 b1 is what? B0 b1 is always refer to the sample data what you have taken, right? isn't it? But when you try to solve problem, you have to solve problem on the population. So what you need to do, again, you have to infer what will be your B0 value and what will be your B1 value for my population, isn't it? What I can do is I can remove this all, and what I will do, say I got B0, I got B1, but what I need, beta 0 is my population B0 and beta 1 in population value. So B0 is my intercept value. Okay, this is called intercept, and beta 1 is called your beta coefficient. Okay, beta coefficient of f is x. So now the example which I have taken, age and relationship. Okay, age and your salary. I can say my salary is equal to beta 0 plus beta 1 age. If you know beta 0 and beta 1 and you give age to the model is going to tell what could be the salary for that person. Okay, so in this equation, what I'm trying to do, I am trying to extract your beta 0 and beta 1. If you got beta 0, beta 1, then you can predict any salary, isn't it?
Actually,
Yeah.
one doubt here.
Hmm.
So when the model is learning on based on some data, so
Hmm.
will it by itself figure out this beta 0 and beta 1?
Yeah.
Okay.
You can do that. Automation, right? That's part of automation.
Okay.
Hmm.
So we don't
Okay.
need to calculate B0 and B1 every time.
No, you don't need to. Even the algorithm is already going to give you beta B0, B1. Now, when
Okay.
you make, hmm. So when you make beta 0, beta 1, these are population data, right? So you have to go through inferential statistics again, isn't it? So when you make inferential statistic, you will be always finding some sort of hypothesis testing, ANOVA kind of thing. Here, the beta 0, beta 1, which we are talking about, it may come with a confidence interval, right? B0 is my sample coefficient, and beta 1 is my population coefficient, right? So this beta 1, what it will do is it will fall under positive or negative with a standard deviation. Okay, that standard deviation is called standard error. Okay, so when you run the program for a linear regression, what you will be finding? Can anybody tell if anybody have run that program? Anybody have run the program in last class? Hmm?
No, like,
Okay, so RL you have, I think, run, right?
Yeah, Lakshmi, we ran the programs, but we were not able to understand the intercept. So, I mean the results of the program.
Okay.
In the program, we found beta naught value beta 1 so that we can, in future, when we get the dependent variable, the continuous variable, we can find the dependent one, if
Hmm.
I'm not wrong, right?
Okay, so let's see. Let me run one program. Okay, so let me share this file. You guys open this one. Just a second. Okay, open this R file and regression. Just open the regression file. Okay, I have loaded another file. Open this one. You guys able to open this file?
Opening it now.
Okay, so open that file, then we'll go through this regression equation again.
Let me just can you show me the path where it is on the drive? Okay,
March
March 20.
2018 regression. I think you guys are
Okay.
not looking into it. Open this
No,
one.
no, no.
Yeah.
I got it.
Election is open.
Okay. Fine. So guys, one thing is for
Lakshmi,
yes,
Lakshmi,
yes. Correct. Yeah.
regression.r, right?
Yes, that's correct.
Yeah. Okay.
Okay. So one thing you have to understand, you have to keep in mind that just like ANOVA, in regression also we have to follow some certain assumptions, right? Fine. There are a list of assumptions like there should be a strong collinearity between dependent variable and independent variable. Okay, because we are restricting the relationship between your independent variable and dependent variable to a linear relationship. Okay, and this linear relationship only will be exist if there is a collinearity, right? Isn't it? Collinearity is a relationship indicating uh, is a feature, right? So what you need to do, you have to first do the collinearity test. Okay, collinearity test says they are strongly related, linearly related, then only you consider. Otherwise, don't consider. Fine. So you have to test of collinearity for all the variables which are there. That is one thing. The second thing is it should follow the normal distribution. Okay, so your independent variable and dependent variable, all the variables should follow a normal distribution. Okay, I'm sure you guys know how to test a normal distribution function, normal distribution hypothesis testing. Yes, right?
Yeah,
Yeah,
Lakshmi.
Lakshmi, you can do a Shapiro test or something.
Exactly. You do the Shapiro test. So what I have done is, so before going to your statistical packages, you can do some sort of exploratory analytics to see whether there is a linear relationship between two variables are there or not, right? You can see mean, median, mode, then skewness, all those things also you can check. This is what I have done. So I put the psych, okay, read the CSV file, okay. Let me see what is there in my CSV file. Uh, okay, household amount charge. Hmm. Now let's describe. So here, what I have, I'm trying to say is, I'm trying to find out a relationship between income and amount charge. Amount charge is nothing but your monthly expenditure. Okay, what is your income, how monthly income, and what is your monthly expenditure? Okay, so see, income is a continuous variable. Even amount charge or the expenditure is also a continuous variable. Fine. Now I'm
Yeah.
going to set up a linear relationship or linear regression between these two variables. For that, two things you have to set up. One is whether both of them are following normal distribution or not, and second is you have to ensure that um, your statistical check like normality test also passed. Okay, what I can do is I can take the separate test. Fine. So I have to describe mean, median, mode. I can see mean is 43. Median is also almost same near to median. Mean also kind of similar. Mean, median, and mode, where I can see the mode. Okay, and I can see the skewness or kurtosis. The skewness is 0.09. It means that it is not skewed. It means it is looks like a normal distribution. Kurtosis also minus 1.3. It is looks like a little flat, right? And similarly for amount charge 39644090. Not much skewed, not much kurtosis. So what I can do is, this may not give a clear picture. I'll put the correlations. Now you can see in correlation matrix, income with household relationship is very small, 0.17. Income amount charge, that is expenditure, is highly correlated, 0.63, right? Similarly, household and amount charge I'm not considering, but they are too strongly correlated. So once you have done that, you can go and plot some box plots. Okay, so box plot also not much. Then plot the line chart. Okay, so I can see from these dots, I can see there is a linear regression exists between your amount charge with your income. True or not? I can conclude from the picture itself there is a linear relationship exists between these two variables. Okay. Further will be I will try to set up the hypothesis testing. Right. Let's run that. It says p value is 0.014. When p value is 0.014, you have to reject the null hypothesis. So what is the null hypothesis here?
My amount charged varies with the income. Or
Yeah. No, the Sapiro test says your distribution is normal or not,
Yeah.
right? Plot says there is a linear relationship between both of them exist, but Sapiro test will say this distribution is normal or not,
Okay.
right? Sapiro test, that's why we were using, na?
Correct.
Right. So it means that first thing is I will try to ensure that there is a linear relationship between these variables exist or not. That I can see from the plot itself. Okay. And once that is confirmed, then I will see whether these data are following normal distribution or not. To ensure that these data are following normal distribution, I will go for a statistical no, algorithm or model which is called Sapiro test, and it is going to help me to say with confidence that this data set follows normal distribution. Now the consumer is following normal distribution, and I can use also QQ and QQ line. See, this is also a straight line. So here my data is following normal distribution. Okay. Once this is confirmed, what I can do is I can set up the linear regression equation. So to linear regression, just call LM. Give the y variable name tilde mark with your list of x variable names. Here in this list of x variable, I have taken only income,
Income.
right? Yeah.
Yeah.
Let's run this. Let's plot the output. So here, how many coefficients I will be getting? I will be always getting two coefficients. Isn't it? What is that? B0 and B1. Okay, B0 plus B1x. So this B0 value it have given 2204, and income it has given 40. Right. Now plot the summary. When you plot the summary, what it is giving? Hmm. So it have given your residuals. You can leave this one. What you need to do is you have to use the intercept income. Okay, and then it is given the point estimated value, and it has given the standard error, and it have given the t value. Okay, so your max and min will be your point estimation. Point estimation is always say z0 plus t standard error. It will be plus or minus. Okay, so here now I got estimated value is 2204. So I will put 2204. Okay, plus or minus. What is my t value I got? T value I got 6.66 multiplied with error 329. See this. This says this is what? Beta coefficients, population value, isn't it? This is what, right? Estimated value. Now you got B0, Z0, whatever is yeah, B0 plus T sigma standard error. So your point estimation is how much? 329 plus or minus T is how much? T is 329. 329. Sorry. 329. T is 6.69. Okay. Can somebody help this one? 329. Hmm. 2401. Okay, so it says this is what the bit is 0. So when you make a plus, it is a huge number. When you make a minus, it is a small number. So that is what the range, the beta 0 will be varying when you do a when you do a prediction, right, on the population. Similarly, I can get for the income also. I can get the value of. Now I will do beta 1 is equal to 40.448 plus or minus, okay, sigma t, right? Sigma t. Now sigma is already sigma is this 40.480 plus sigma t. Sigma t is equal to 7.18, 5.6. Can somebody can say that? What is the value? 7.18, 7.18 multiplied with how much? 56, 402. So 402 means 42. Okay, this is what the beta 1 value. So you got beta 0 value, you got beta 1 value, and finally you will be deciding what is that value of beta 1, beta 2 you can take, which is going to give you the best prediction. Okay, this is again an iterative process to find out. You have to give all the combinations and try to get the best possible value. Okay, this is how your coefficients are interpreted, coefficient, then how your residual values are interpreted, right? This is how you will be using it. Any doubts here?
No, Lakshmi.
Hmm?
No,
No,
I
Rashmi,
didn't.
continue.
Okay, so now you guys are able to understand how to interpret the variable outputs, our linear model regression outputs.
Yeah, sure.
Okay, so quickly do one thing. I have given another example. Just go through it. Okay, take a 5 minute, go through it, and then there is another problem which have a multiple regression. See that problem, and we'll come back. I'll come back in 5 minutes and take you through that. Okay, look into this code first. Okay, so all of you have gone through the example.
I was going through the code, Ashwin, just checking it out.
Okay, okay.
actually, the correlation, the function which we have used to find the correlation, right? COR.
Hmm.
There we in the result we got a matrix.
Yes.
So income is always one. Okay.
That is always one with
So
yourself.
now, how to interpret this income and household, which is 0.17 like that? What actually does this 0.17 mean?
Correlation, see, correlation is we have tried, we understood covariance, right?
Yeah.
So covariance says when there is a large change happens in one variable, how it
Okay.
is affecting to the other variable. Okay,
So
the variation in one.
is it kind of a rate at which income changes when a household change?
This is what it is telling. So the collinearity, I mean correlationship, what it is just giving is how they are related to each other. They are related strongly or they are related weakly. So if it is, and the correlation is always in the matrix of -1 to 1.
Okay,
Hmm. So
got it.
when there is a strong relationship, you will find it will be
One, one.
near to 1 or near to -1.
Okay.
So near to 1 means it is strongly related in a positive way. When there is a change happens in x, when there is a change happens in x, there is a positive change happens in y. Okay,
Yeah, correct.
and the negative correlationship is similarly. Okay,
Okay, got
when
it.
there is a change happen in x, the negative change. Hmm.
Yeah, got it.
So yeah, so that's why you will find -1 to 1. Okay,
Got it.
if it is near to 0, it means that there is no.
No change. No change.
Yeah. Okay, you
Okay.
can check the core function documentation also.
Yeah.
Hmm. It is coming from correlationship.
Uh, we are not able to see your screen actually.
Oh, sorry. Now you guys can see it,
Yeah, it is fine.
right? Hmm.
Yeah, I got it.
Okay, so this word. Now you need to run covariance matrix, ensure that there is a relationship exists. If there is no relationship, I think there is no point of running your regression equation. Okay, so then there is a normal distribution check. Okay, I run Shapiro test. Once it is done, then you run the simple regression. Okay, in simple regression, you will find coefficients beta 0 and beta 1, their point estimation, uh, and your range, right, interval estimation, right, because the data what you have taken is a sample data. That's why you will be getting b0 and b1, but you want to estimate your population parameter, nothing but beta 0 and beta 1. So beta 0 beta 1 point estimation it have given, it also it have given standard error and t value. Okay, standard error and t value, if you multiply them, it will give you plus or minus of interval estimation. So that's what the point of. Hmm. There is something called residuals. We'll understand what is residuals. So residuals is nothing but the total error, isn't it? So what is minimum residual? What is median value of it? Okay, what maximum residuals? Then what is residual coming under first quarter? First quartile in the sense first quartile in the sense first quartile of the data set. Okay, in the third quartile, what is error? You can see in the first quartile you see negative, and third quartile you see positive error. Okay, so your residual must be small, right? Your residual should be always small. How small it should be, that is also we need to know. How I can see residual standard error? Residual standard error is 731. Okay, multiple r square. Multiple r square is nothing but multiple r square adjusted r square. So adjusted r square is nothing but the sum square of error. Okay, what is multiple r square? Let's see that. Hmm. Hmm. So you understand adjusted r square, you keep it multiple r square, then f statistics, okay, and p value. Just keep it. You understand coefficients and adjusted r square. Okay, rest of the thing we will understand. Residual is anyway, that is the error part. We'll understand what is a multiple r square and residual standard error value. Okay, when we go to multiple covariant factors, multiple linear regression. So here, what is multiple linear regression? Can anybody explain?
Where we have multiple
From that code
variables.
variables,
Mm-hmm.
dependent
Instead
variables,
of having two
independent variables.
variables, we will have
Multiple variables. So how I can represent that equation?
instead of
Something
beta
like
1 and beta 2, we will be having beta 2, beta 3, beta 4, like that. It will go up to n number of lines.
Okay. So how? So what are the assumptions I have to maintain?
the distribution is normal.
Hmm,
There is no correlation between the variables.
Okay. Independent or dependent?
Independent.
Independent. Independent.
Okay. Hmm. And
We should take least number of the variables by which we can predict the values. So we have to neglect the variables which are going to the same direction.
hmm anything else? That's it, is it? Okay. So please remember that cosine of r square assumptions. Hmm. Hmm. Okay. So this is what r square we are getting. Hmm. Adjusted R square is nothing but this is the one. Okay, and always is okay. So a large R square value should not be interpreted as meaning that estimated regression line fits the data well. Okay, another function might better describe the trend in the data. So if you get a larger R square, it means that it is not a, it is the regression, the relationship is not fit for linear regression. It could be something else. Okay, the coefficient of determination R square and correlation coefficient R can both be greatly affected by just one data point. Now see here, there is something, a twist is coming to picture. Now you understood what is the significance of R square, isn't it? Now let's see in my equation how I can get a issue because of my quality of data. So everything you understood, b0 beta 0 beta 1, point estimation of beta 0, point estimation of your beta 1, all those things are fine. Okay, now I will be always trying to have a minimum R square value, adjusted R square value, some square of error. So how this will be minimized, or how it will be giving a conclusion that my R square value is small and I can have a good prediction. For that, we need to understand what are the factors that influence towards R square. Okay, so like this, I got the equation, I want some data points. Okay, so I can have a line like this, isn't it? True, right? Yes or no?
Yeah.
No, is it? Okay. Now I also got another line like this. There is something like this, something like this. See here, here it is following a straight line, but there are 2 points are here. When I try to um, adjust a best fit line, what it will do is the line will be slightly deviated towards like this, because the line is trying to minimize the error, and it can see the maximum error is coming from this line, so it will make a tilt towards the points, toward these points. What are these points? Can anybody tell me?
Outliers.
Who have answered this?
Karthik.
Karthik. Okay. What about others? Aril, Sunil, Sasi, Vinod.
Yeah, Lakshmi, I'll outliers only.
Who is this? Sasi, is it?
No, Vinod.
Okay. Okay. Great. Yeah. So this is what you can see, guys. I mean, if there is a presence of outlier, now your entire line equation is completely changing, right? When there is a shift happens in the best fit line towards your outlier, your beta values will be
Incorrect.
it will be incorrect, right? So though you will be getting r square, small r square, but it is not only r square is going to give you the best prediction. So what you need to do is you have to also ensure that the data what is there, does it making sense to build the model. So you may be finding some data which are actually irrelevant data, okay, or they are completely away from the data what you have. So you have to make sure that you have to make a outlier inspection or
Treatment.
outlier detection. Yeah, outlier treatment. And then you go for having other assumptions like normality and blah blah blah. And then set up and then find out R square value. Based on R square value, you take a call whether you should go for linear regression or you have to go for something else. Got it? So this is
Yeah.
what it is trying to tell you. Okay. And the list of assumptions, mean of the response EY for each of the predicted xi is linear function of xi. So you try to build a relationship between each independent variable with the dependent variable and see all these equations are linearly related. Okay, otherwise there is no point. Then error are independent. Now the error are independent means now x variables have some relation with each other, like some students have a cheated answer, residual versus ordered plot, but we need to know the order in which data is collected. If E0 are not independent, then estimated standard error tend to undermine the true standard deviation. Predicted value would be negative. Okay, so the third one, what it is saying is the error E0 are independent. So error E0 are independent means now if I take first 1 month data and build a regression, I got one error, and then I took next 1 month data and build that model and I got another error value. Now let's see, you when you plot all these errors, there should not be any such of relationship, right? Okay, these errors should not pose any sort of relationship. It should be completely random. Then only your linear regression is working. Otherwise, it is not working. Okay. The error is each value of the predictor xi are normal distributed. It is also telling the error should be random in nature and also it should be normally distributed. So how you will get the error? Now from each x you can get a y predicted value, right? And then you also have a y actual value. Now y minus y actual is nothing but your error. Okay, now if you take this error values of all the rows, you can plot them and see whether it is looking like a normal distribution or not. We can do that, right? Isn't it?
Yeah, Lakshmi.
It is clear or not? See, these
Yeah,
are the
Lakshmi. Clear.
assumptions. Yeah, these are the assumptions you have to ensure that you run for all the models here. Okay. First thing
Mm-hmm.
is this should be linear relationship. Second thing is errors. What you need to do, you build a model and there is no relationship between error 1 to error 2. Then third thing is error each level of rated xi are normal distribution, that error should be normally distributed, and normal distribution in the sense it should be randomized. Error each value of predicted xi have equal variance of y. Residual versus fitted plot depicts the shape of error term with respect to. Okay, so you can for leave this one. So main four things you have to, all the distribution should be normal distributed. Okay,
Mm-hmm.
the errors between one event to another event should be independent, and the third one is what, and the third one is you have to make sure that you treat the your outliers and ensure that you have the linear relationship between your x and y. So if these three are satisfied, I think you should go ahead and build the model. Otherwise, you should not. Okay, this is what all about the linear relationship, because I have to rush through because you guys have already spent some couple of hours on this, right?
Yeah, Lakshmi.
Uh, So this is what I have also given the sample data, and then I have given another the multiple linear regression problem. Okay, so you take that depression score with medical, run that linear regression, and tell me what is your observation. And then we also have a promotion data set and in-store promotion, and this is also you run and let me know the result. Okay, depression. Let me upload the depression scores. Yes. Okay, depression it will not run because even promotion cell also will not run because I have not shared the data. Okay, so guys, you do one thing. Uh, yeah, the data set is not there. What I'll do is I will drop those data set as an assignment, but immediately let's go to the multiple linear regression set. Okay, in multiple linear relationship you will be finding always when you try to predict the salary. So will you be considering only age? What are the factors to influence your salary?
The experience, as well as the domain or department which I'm working in.
Qualification,
company you're
Okay,
working for.
the
yeah.
area at which we are working.
Uh-huh. And your experience also, isn't it? Age is
Also,
one thing.
I think the currency, like where you're working, which country you're working.
Mm, right. So what it is telling is if you have something multiple, I mean, independent variables, then what you need to do is you have to establish a multiple linear relationship. But the problem is for multiple linear relationship, you have to ensure that your independent variables are not related to each other. They are having only relationship with the dependent variable,
Dependent variable. Yeah.
right? So
Yeah.
how I can plot it? Let's say I have taken a very simple example. You see here multiple linear relationship. The amount charge is nothing but is a function of income as well as household size. So how much you spend in a monthly grocery depends upon what is your salary and what is your family size. Yes or no? True, right?
Correction.
Right. So similarly, any other examples, guys, you have already given. So what we can do is I can take up another example here, auto data. Okay, let me put all this thing. Hmm. Okay, so guys, I have given one auto.r and auto.csv. Okay, upload that files, run that, and then we'll go to multiple linear regression and its challenges. Okay, run that one.
Lakshmi, what is this variance inflation factor?
Rashmi, this VIF package is from VIF function which package exactly?
So multiple linear regression, you guys have already put it right. Auto, I also uploaded the auto data.
Yeah, Lakshmi.
Okay,
Yeah,
good.
Lakshmi, I've got that data. So there is one term called variance inflation factor.
You
What
don't
actually
go
it does?
don't go to the variation inflation factor. First you understand the data. Okay, first we will talk about data and then we'll go to multiple linear regression and the problems of multiple linear regression.
Okay, okay, fine.
Yeah, first read the data, what it is talking about, what is that we are trying to predict. Okay, and then we'll look into it. Hmm. So you guys have gone through that PPT and the dataset, right?
Yeah.
Okay, so multiple linear regression is what nothing but when you have multiple independent variables having independently a linear regression shape with the dependent variable, isn't it? So
Yeah.
what it is trying to say is somebody is traveling in car or bike, is it? Okay,
No,
now it's
Lakshmi.
better. Okay, yeah, I hear some, I mean, the bike sound.
Yeah.
Okay, fine. So here, let's say I have taken, okay, so what is that car example? Miles per gallon, right?
Actually, I'm
Isn't it?
not able to
Oh,
see
sorry,
your screen.
sorry. Yeah, sorry. Okay, so my car example says miles per gallon, right? I mean, uh, so what are the factors uh, are going to influence the vehicle fuel efficiency? Isn't it? This is what I'm trying to predict, right? Now, say I have to buy a car, right? So if the engine power is high and the engine, I mean, the car weightage is high, then you will find the weight of car have a negative relationship with negative linear relationship with your um, your vehicle's fuel efficiency. Hmm, true or not?
Yeah.
Similarly, say the second one is, let me open the data set. Where is it? Where is it? Yeah, this is my data, right? This is my miles per gallon. So I have cylinder, I have displacement, the horsepower, weight, and acceleration, right? And this is my miles per gallon. You see, all of them are continuous variables, right? So cylinder, displacement, yeah, this is also, I mean, it's a continuous, right? It is not categorical. Hmm. So displacement is also continuous, horsepower, weight, acceleration. So, and my y response variable is mpg. Now, what I am trying to find out is, so whenever there is a change happens in cylinder, okay, there is a linear change or positive or negative change happens in the miles per gallon. Similarly, with the displacement, horsepower, weight, and acceleration. Each individual independent variable is linearly related to your MPG. Okay, either in a positive or in a negative way, right? So the multiple linear regression, okay, so y is equal to, how I can represent m or beta 0 plus beta 1 x plus beta 2, sorry, x1, beta 2 x2 plus beta 3 x3, right? And says when there is one unit change happens with x1, okay, when x changes beta 1 units change in y, okay, when 1 unit change happens in X. Now B1 units change happens in Y, and no change on other variables.
Lakshmi, 1 unit change
Yeah.
in X1, right?
Yes,
Not F.
X1. So when there is a 1 unit change happens in X1, it have only impact on Y by B0 unit of X1. Okay. And there is no impact on X2, no impact on X3. If that is the case, then I can represent the relationship between or among those X1, X2, X3 with Y like this. Okay, but this is what the assumption, right? Assumption of what? Multiple linear regression. Okay, this is what the multiple linear regression equation. Okay, now if there is any violation, then this is not going to hold. This you have to cancel it. You cannot take this model and try to build your predictive analysis, right? You cannot do that. So what it says, since it's assumptions, you have to hold it. To hold this assumption, what I need to do is there any relationship between or among those independent variables are there or not? I will try to find out. How I can do that? I can simply draw a collinearity matrix, right? What I can do, so here I got my cylinders, displacement, horsepower, weight, and acceleration. So these 5 variables, I will try to draw a correlation matrix. Okay, covariance matrix or correlation matrix, and try to see if any of them have any sort of linear relationship. If there is a linear relationship, then definitely not linear relationship. If any kind of relationship is there, correlation is there, then it is going to impact on my prediction. Okay, so this is what I'm trying to do it. If you see the car example, I have uploaded R also, right? R code also uploaded. See guys, I mean, now it will be easy, right? See, all this predictive modeling R code is very straightforward. What you need to know is you need to know the steps. Okay, what are the assumptions you have to do, because these are all maths, isn't it? And math is working on some kind of formulas, right? And formula expects you some kind of uh, limitations, like if it is a equation y is equal to mx plus c, if there is a linear relationship there, then only you can uh, convert it to a equation, otherwise you cannot do that, right? Similarly, multiple linear regression also, we found that there should not be any impact on other variables when there is a change happens in one independent variable except your dependent variable, isn't it? If there is any change happens, then it is a violation. It is a violation and it is not going to help you to build the model. Okay, this is what I'm trying to convey to you guys. Okay, you take this example. I have run this. Okay, fine. This is Autodata is clear. Now just okay. So this correlation matrix I have plotted. In the correlation matrix, I can see miles per gallon with cylinder is very strongly correlation with minus 0.85. and miles per gallon with the displacement is also strongly correlated. You see here that there should not be should not be any relationship between independent variables, but here I can see there is a strong relationship between some of the independent variables. So my first assumption of uh, independence of variables are I mean broken, right? So I cannot use multiple linear regression. I have to do something else. What could be the other approach of something else? What I can do?
Linear regression for each variable, I mean, against the y, for each x against the y.
Hmm? It's no, I didn't get that.
The linear, like we will do a linear regression for each x1 against the y.
Huh. Okay, then I will add all of them. Is it?
Uh, might be correct.
No, then you have not understood what I have been trying to explain. I have told that suppose I represent y is equal to, okay, this is what, right? Beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. So when there is a change happens in x1, 1 unit change. So y changes by how much?
Beta 1.
Ah, beta 1.
Beta 1 unit,
Good. X2 changes by
1
huh,
unit.
what?
2 units.
Sorry, beta 2 units.
Really?
Okay, okay. There is
X3.
there is no correlation between these variables.
Hmm. Okay. So if this condition satisfies, then only your multicollinear relationship, valid. Otherwise, it become invalid. Now say when x1 changes by 1 unit, okay, there is a small change happens in x2 also. Small changes, okay, some delta changes. Then
Mhm.
now what I am trying to do here, this y is b0 b1 x1 plus b2 x2 plus b3 x3, right? So if beta 0 is a constant term, right? This constant term I can have say something like v1 v2 v3. So what it means is like b1 plus b1 x1 plus b2 plus b2 x2 plus b3 plus b3 x3. So it is saying that they are independent, okay? So if there is any change happen in x1, it also have an impact on x2, then the y value will become what? Y value will become 1 unit change of x1 will become your b1. Huh? Y change will happen b1
Plus
of
b2
b1 plus x1 and delta of x2. Similarly, when x2 change, there is a change that happens in uh, x2, then it will be how much? let's say only there is a multicollinear, I mean there is a relationship between x1 and x2. Okay, when there is x1 change happens, there is a delta change happens in x2. Okay, when x2 changes, let's consider that there is no change happens in x1. Okay, then here it will be only beta 2, and here it will be only beta 3. So the entire equation becomes, so this is not something I should teach, but anyway, y is equal to say beta 0, okay, beta 1 x1 plus delta x2 plus beta 2 x2 plus beta 3 x3. So this delta x2 change will be always missing in your multiple linear regression, right? So that's why what it is saying is there should not be any relationship between x1 x2 or x1 x3 or x2 x3. If such relationship is there, then your multicollinear function, I mean multiple linear function, is not going to hold out. Okay, you have to remove that multicollinear relationship among your independent variables. Okay, so how I can see whether there is a relationship is there or not? Simply draw the core function, simply call the core function, correlation function, it is going to give you. Okay, clear?
Yeah, Lakshmi.
Yeah.
Yes,
Okay,
Lakshmi.
so now what are the remedies? How I can get rid of I mean such problems? Whether I know these are the important variables I have to take, but unfortunately there is a multicollinearity problem. Multicollinearity is nothing but one variable have a relationship with multiple other variables. Multiple variables in the sense, say, let's say when I take the example of here, uh, hmm, what are the variables? Tell me. Cylinder, displacement, horsepower, weight, and acceleration. Now, cylinder have a relationship with the displacement and horsepower, and displacement have relationship with weight and acceleration, and horsepower have a relationship with acceleration and displacement. So in this case, one variable is interlinked or it have a relationship with multiple variables. That becomes multicollinearity problem. Okay, so if there is a multicollinearity problem, it become more complex. And your multiple linear regression is not going to work. You have to take some actions. Now you guys have to answer me what are the actions I will take. Go ahead.
Lakshmi, if the variables are relating very correlating to each other, maybe we can reduce them or combine two into one or something like that. If they both are behaving the same way.
Yeah, please, all of you, one by one, just give me answers.
Lakshmi,
Yeah,
I think,
Lakshmi, can you
yeah, go
hear?
ahead, Arun.
Yeah, so if the variables are dependent on each other, like okay, so for example, if displacement is when our displacement changes and there is a change in acceleration also, and if they're changing linearly to with among themselves, maybe we can club them together and get a single variable.
Okay, so yeah, Karthik, go ahead. Karthik.
Like if two independent variables are changing, yeah, two independent variables are actually depending on each other. So again, then we have to consider a linear equation among them. Is it correct?
Linear equation between whom?
Between the two independent variables, and from that find out a best fit possible, and then
I don't understand. You understood linear regression properly?
Yeah.
What kind of problem I'm trying to solve in this data set?
So here my independent variables also depend on each other. So
No,
this is the problem.
no. What is this problem here? Here, I am trying to predict, okay, the miles per gallon for a vehicle whose configurations are like 8-cylinder,
Yeah,
360
correct.
displacement, okay,
Yeah,
175 horsepower, weight CA21, acceleration 11. Now, at
correct.
certain point, I'll get some configuration, and I'll try to predict what should be the miles per gallon for this vehicle.
Sure.
Right.
Correct.
For example, you want to buy a vehicle here, okay? So you want to buy a vehicle, and you are very much conscious about the miles per gallon. Now, what you should know, which will help you to predict or to find out what should be the miles per gallon for the vehicle. Okay.
Correct. Correct.
Now, this is a very good example of a multiple linear regression, isn't it?
Yeah.
Right? The problem
Correct.
is here the multiple linear regression should. Oh, there is a background noise there. Whose noise is that? Okay. So here what you need to do is you have to build a multiple linear regression. But in the multiple linear regression, I found there is a multicollinearity problem exists, isn't it? And because of the multicollinearity problem, whatever I am going to do the prediction, it is not going to give me the correct answer.
Correct.
Yes. So in this case, what I am going to do, the first thing is I will try to see how I can eradicate that multicollinearity problem. Right. To remove the multicollinearity problem, I can have a multiple choice. One thing is, whichever variables are creating more problem for me, let me remove them first. I can do that.
Yeah.
Hmm?
Correct.
And then, yeah, then and see how much accuracy it is increased. Okay.
Mm-hmm.
And then you can keep on going on removing each variable and see whether there is an improvement happens or not. I can
Yeah.
do that, right? Let's say
Yeah. Correct.
there is only one variable which is creating a big the most problem. Let's say the horsepower is one variable which have a multiple collinearity among all the variables with a greater weightage. If I remove that horsepower, then the remaining variables like cylinder displacement, weight, and acceleration have no multicollinearity among themselves. Okay, then the model is going to work out, isn't it? Now I can get the prediction of MPG based on the values of cylinder displacement, weight, and acceleration, right? I'll get it, but the point is, in domain point of view, whether horsepower making sense of keeping for predicting MPG or not. If horsepower plays a very important role in predicting the miles per gallon, then you have to retain it. You should not drop that variable in order to fit into the multiple linear regression. Okay, because multiple linear regression have a constraint or constraint of that all the variables should be independent. To maintain the variables list independent, you should not go ahead and drop it. Okay, dropping any variable is not a good idea. Okay, as long as your accuracy is concerned. So what you need to do is you have to try out other alternate approaches. The other alternate approach is nothing but something called principal component analysis. Okay, so what it is doing is it is going to create some orthogonal principal components which are completely independent to each other. So it will take all these variables, it will regenerate a set of orthogonal variables. Orthogonal, you know, right? Completely independent
Yeah.
to each other. Okay, it will create those orthogonal variables and you will take those variables to build a multiple linear regression. Okay, so that's what the PCS is all about. Here somebody have put one question, right? What is that you guys have? There was one question came out, I don't know, VIF, variation inflation factor,
Okay.
variance inflation factor.
Mm,
Variance
mm.
inflation factor we'll talk about, but I just wanted to know, you guys have already understood the PCA or you have to understand again?
PCA we haven't done, Lakshmi.
Okay, not a problem. So till now you understood what is linear regression, what is multiple linear regression.
Yes, yes.
Okay, I'm going to release some assignments and you guys have to study few more things and then we will take PCA in the next class. Okay, PCA and factor analysis, we'll take it in the next class.
Okay, Lakshmi.
Fine. So is there any doubts and questions? Just float it now. I'll have another 5 to 7 minutes. I'll take off your questions. Any
No, Lakshmi,
questions?
nothing from me.
Okay. Yeah, Karthik.
Yeah, Lakshmi, I mean, so far clear, but I have to do some hands-on. I mean, both in R as well as from problems.
Huh.
So
So
I'll get back to you if I have anything.
yeah, whoever have the books, please go through the book. Okay, I have also say some of the no data sets. Please look into the data sets. Okay, now onwards your R programming is going to be very straightforward, because this is all straightforward programming, because okay, uh, it will be majorly in 4 steps: data clearing, I mean data cleansing, okay, data preparation, where you have to do some sort of aggregation, and because most of the models what we are going to handle is it will be purely on the um, prepared data. Okay, I have already taught you how to prepare the data and how painful it is. Both all of you have gone through the project. I don't know, some guys are no almost kind of completing their data preparation, but I have not heard about Sasi, Sunil, and Vinod. Where you guys and what you guys are doing? Okay, whether you guys are really working on the project or not. Hmm. So you have to come back and tell me what you are doing. Okay. So data preparation part is almost clear. Okay, how to prepare data, how to build a relevant data set for your model. Okay, now onwards always there will be certain tweaks and tunes, uh, and most of the time the data will be in a prepared data set, but now the focus will be more into the model. Okay, and the assumptions and the areas of investigation and how to interpret the results of the model. Okay, so once the machine learning is over, then we will get into the deep learning. The deep learning is going to do the same thing what your linear regression or multiple linear whatever it is doing, because our brain is tuned to do any sort of work. That's what the deep learning is all about. But before getting into that, we will complete all these packages. Okay, so next class it will be PCA, and then it will be factor analysis. Once PC and factor analysis is done, then we'll go to your classification problems. Okay, so another 2 classes will complete regression. Fine, guys.
Yeah, Lakshmi.
Okay.
Yeah, Lakshmi.
One more thing, I need to release 2 more assignments. One is for ANOVA and one is for multiple linear regression. So guys, you make sure that you get it done by this week.
Sure, Lakshmi.
Yeah, Lakshmi.
Yeah. Okay.
Lakshmi,
So
what is the classification problem you told?
classification problem we'll talk later. Okay. First you work on ANOVA and regression first. Okay.
Okay.
We'll teach you everything. Okay. But don't jump here and there. Ensure that whatever no chapters, whatever subjects we complete in the class, you go through them, understand them, and then make sure that you're ready for the next class. You don't jump here and there. Okay, that's why I'm not telling you the course content, all those details. You just believe us and no, ensure that whatever is needed in the market, okay, what is there actually data scientist or data analyst working in the industry, we are going to teach you guys. Fine. So don't try to compare the content what I am teaching or what our guys are teaching. They are relevant or not, or they are different from other institutes or not. Don't try to compare. I'm ensuring that you learn which will help you to get into the job. Okay, this is what I meant. Okay, guys. So books you study. I also recommend another book that is called Predictive Analytics with R. Okay, I will give you that one. Okay, because now we are going to start the predictive analytics, right? So this book also you try out. I'll give you the 1 second. Okay, so the picture is on the WhatsApp. Okay, sent. So try to buy this book. This is also one of the recommended predictive analytics in R, which may help you guys to have good number of hands-on. Okay.
Okay, Lakshmi. Thank you.
Yeah.
All right,
Take it,
Lakshmi.
guys. Yeah. Okay then, guys. Yeah. See you on the next week.
Yeah, see you, Lakshmi. Thanks. Thanks for the class.
Thank you.
Lakshmi, hello.
Thanks, Lakshmi.
Yeah. Yes, Sasi,
Yeah,
please go ahead.
assignments.
Ye-
You are telling.
Yes, assignments I will submit for ANOVA as well as linear regression. Maybe by today night
Okay.
or maybe tomorrow morning. Okay.
Okay.